Okay, should be recording. Give it a minute, make sure. All right, so we're recording now. All right, so welcome back. Good old CSE 204, Database Management Systems. Today we're going to be talking about normalization. So we introduced it last week. We introduced it on Tuesday. I'm going to review those again because of this is kind of an important concept. We'll spend quite a bit of time. We'll spend quite a bit of time today on normalization of getting from an unnormalized database into what's called the third normal form. So we're going to review some stuff that we did on Tuesday of last week, and we'll do that again because it is important to understand the foundation of functional dependencies and how that works. And yeah, so we'll do that. And then we'll move on into it, into actually how to do the process of normalization. We are probably we're going a bit faster than the syllabus has said, and I think a big part of that is because I think I've kind of looked at it, and it looks like we're going to end up needing more time for group presentations than was originally scheduled because this class is bigger. This class is bigger than it has been in semesters past and years past. And so because of that, there will be more groups, and because of that, I don't want to shortchange you. I don't want to give you less time to present than you really deserve. Okay, and so because of that, I think we're going to have to do an extra week worth of presentations than originally planned. And so, but you know, I'll do the math on it to make sure, because I want to give you as much time, and I want to give as much commitment and energy and time to these things so that you can know how these concepts work and how this stuff does. Okay, let's go ahead and share the slides. All right. So here we are, normalization. First thing, actually, I do have a quote. I have a quote today. I know I'm not been very consistent this semester with this, have I? But I figured a Shakespeare and Lincoln quote. So those of you who everyone should know who William Shakespeare is, right? This is not a. I mean, there's a restaurant named after him here, right? In Turkey. I don't know if that's a global restaurant or not. And then Abraham Lincoln was probably maybe the best United States president that we've ever had, but I don't know. I don't know how to grade them. But William Shakespeare says, "A fool thinks himself to be wise, but a wise man knows himself to be a fool." So we need to be careful, make sure we know that we understand that we don't always know everything, right? That we can learn from our lack of knowledge. So that's part of what learning is all about, is understanding that what I thought I knew may not be really accurate. All right. And then Lincoln tells me, you can fool all of the people some of the time and some of the people all of the time, but you cannot fool all of the people all of the time. So this is more about kind of politics and how to convince people of things, but you know. All right, so just some fun quotes there. There was a follow-up. I remember somebody told me about the Lincoln quote that said, you can fool all the people all the time if it's an election year. So if it's a time for elections, but I don't know how true that is. All right, so just some fun quotes, some fun things, right? All right, but what we're here to talk about today for real is normalization, right? And some of the key parts of what we'll talk about is this idea of functional dependencies. All right, understanding what a functional dependency is. We talked about this on Tuesday, but I would like to go over it again because it is an important concept. All right, and how to identify them. We'll talk about that today. All right. how we can use our functional dependencies to identify the primary key or a candidate key, those kinds of things. How to process normalization, how to commit, how to how to perform the process of normalization. Again, the whole point of this is we don't want to just make our database willy-nilly. That's a phrase that you guys probably don't understand. We don't want to make our database ad hoc. If you know anything about software process, you know the ad hoc process. We don't want to just go randomly, let's just create tables because that's what seems to make sense. We want to have a systematic approach of how to take a set of data and break it up into its normalized database tables. And the way we'll do that is through this process of normalization, where we identify functional dependencies and then use those functional dependencies to understand what should be new tables and what should be our core tables and stuff like that. Okay. All right. So let's, again, we'll talk about some of the benefits here. I talked about this last week, so I won't go over this too much again. But the whole point is we're trying to get minimal redundancy. We don't want to have a bunch of data that's redundant, right? An attribute represented only once, all right? And the reason why, again, is because we don't want to have duplicated data that could be one thing in one place and something else in another place, a certain value in one place and a different value in another place. You know, this actually, it's interesting. This problem, if you will, has come up a few times, even in our courses here at the university, because, for example, let's say that OBS has your name written a certain way. OBS has your name written the way that you registered for the Octanese University system, but then maybe it's different in another place. So this was especially back before we were on this Microsoft Teams thing that directly connected to the university. But whenever we were using like Google Classroom, right? Some of you, your Google accounts, your name is spelled differently in the Google account than it is in the university account. And so for us, we had to go and kind of like figure out, okay, who is this? What is this person? You know, and try to make a connection between those two. Okay. So what if the same was true in a database that was part of one system? Let's say in OBS, your name and your student number maybe was one thing, or particularly your name. Let's say your name was one thing, and then in another part of the same system, your name was spelled differently. You know, we might have some problem there, right? There wasn't data consistency. And what that suggests is that if that is the case, if we have situations where a piece of data is one value in one place and a different value in another place, it suggests that we have duplication of data, right? Or data redundancy, right? And that could be a big problem. Okay. Another good thing is taking up that minimal storage space. You know, the example I gave was the thumb drive last week. That storage space is like, we don't really think about it anymore because there's just so much space available to us. We also don't think about processing speed as much as we used to because things fly by, things are happening so quickly in a computer system. But this is still something that we still should think about. We want to take up minimal storage space, especially because, so for your databases that you're making for your project, you'll probably only have, you know, maybe a 100 or so rows that you're dealing with as example data, and that's fine. I'm not going to ask for much more than that, but I'm not going to ask for more than that. But do you think about a database like Hepsiburada or Sahibinden or Amazon or, you know, anywhere like that stores a bunch of stuff in it, Okay? That we're talking about millions upon millions of rows that they're having to deal with. Right? So they are wanting to make sure they take up minimal storage space to be able to access things quickly and easily. Okay. All right. All right. So we talked about this. You know, one of the big things we also want to reduce, well, by having data redundancy, is we reduce what's called update anomalies. We talked about the update anomalies being that what they are is there are these things where if I update a piece of information in one place, but it should update in multiple places, that could be an update anomaly. So an example here would be like this. We talked about this, where let's say we had this staff branch relation, where notice that for B005, this 22 Deer Road, London, it shows up twice. And that's okay. I mean, two people work at the same branch. That makes sense, right? But what happens if somebody were to come in here and type in into this address field something else, like accidentally said 23 Deer Road, London, like they tap the wrong button on their smartphone. Okay? And now you have an address for one that's for the branch that doesn't match the address for that same branch in another row. So which one is right? Well, just from the database, we don't know. We don't know which one is right just from the database. Right? But if we were to have it in its own table, then if somebody were to even type in the wrong information, right, that could be checked and that could be changed just this one place. Right? Here, by having them not match, if this was 23 and not, and I could even maybe do it like this, 23. This is hard to do. All right. All right. By having it wrong in one place and right in another, we don't know. We might not even know that there's a problem, right? We might not even know that there's a problem because we might never see this data, right? Whereas here, anytime we access branch B005, we get whatever its address is. And if we find out that it's wrong, we know that it's wrong and we can change it this one place and make it correct. Okay. Again, so the staff branch relation has redundant data, things that show up twice. The details of the branch are repeated, right? And the branch only relation, each branch information only appears once. And so we just use that primary key, branch number, here as a foreign key here, and that way we don't have to have this duplicated information multiple times. Okay. We talked about what updated anomalies are. This was the big thing that I said I wanted to, this is the reason why I wanted to go over this set of slides again, is because I want to make sure that we understand what a functional dependency is. Okay. So a functional dependency is any time that one column, its value is dependent on the value of another column. All right. Anytime one or more columns is dependent on the value of one or more other columns. All right. Let's see. The way that we draw this is this A determines B. Okay. Well, I'm trying to figure out how to connect this thing because I want to. Okay. All right, so the way that we would draw this is A determines B, and what I'm going to do here Let's see, where are you? Okay. I want to draw it out like this. All right. So the way that we can do this is we can say, let's say that we had okay, like a column A, column B, column C. Okay. And there are some values here. Actually, let me go ahead and actually put real values. Okay, like this, right? Where these are my rows, right? Now, what we can look at here is we could say that it looks a lot like the value in A determines the value in B, right? That's what it looks like. And that would be a good assumption, right? And so the way we would write this is we'd say A determines B. Okay. You could also read this as B is functionally dependent on A. Okay. Now, what about C over there? Okay. Does A determine the value in C? Yes or no? What do you guys think? Right, A does not determine C because A, the value is 1. Let me change the color here. Right, 1 here gives me 1 here, but 1 here gives me 3 here. So nope, that does not determine. That's an automatic. We automatically know that A determines C is not right. Okay. What about B determines C? What do you think? All right, no again. All right, and what we're going to learn in just a moment is if A determines B, right? If B were to determine C, this would be called, we're going to find that in just a moment. This is called a transitive dependency. And if this exists, then the transitive property says that this must be true. Okay, but since this is not true, then this is not true either. Okay. Well, or yeah, it could be, but all right. Since this wasn't true, this cannot be true either. Okay, so that's not right. All right. Well, what about going the other way? What about C determines A? What do you think? Is that true? Oh, Torana, the reason why we didn't necessarily say that, it is true that 2 gives me a different value. But because there's no like other row down here, we don't know that one for sure. But what we do see for sure is that when a 1 shows up in A B shows up in B. We know that to be true. Okay. If there was a 4th row down here that was like 2 and I don't know, S right there, then we would know that this is now not true. But since we don't have that as an example, anytime, there you go. anytime we only have like a one row thing like this here, we don't know we can't determine functional dependencies based on that alone. But because we have this here, because we have a pair, like more than one time that this determines this, right? Then we can base it off of that. But if there's only like a one row example, we can't really base any functional dependencies off of that. Sorry. All right. Where were we? So, okay. All right. So, by the way, in this particular example, because it's such a small one, we could also say B determines A. That is also possible. Right now, because they are the exact same, we don't know for sure. Okay. What about C determines A? What do you think about that? Or C determines B for that matter? Okay. It is possible. Okay, so those of you who said yes or true, Okan, or yeah, nice, maybe, all right. It is possible, but based on this small set of data, we don't really know for sure. Okay, because each of these is unique. This is different from this is different from this. We don't honestly know for sure. The C is, in a sense, C is kind of acting like our primary key for this table, and so we don't know for sure. You know, what we do know for sure is that because this combination here is the same and this combination here is the same, but the C value for both of those is different, we know that neither A nor B determines C. We know that for sure. Okay. All right. So I'm having fun playing with my little drawing pad application over here, but let's move back to the slides. Let's see if this works. Okay. All right. Okay. So again, the way that we draw that is we can say A determines B. We could also say B is functionally dependent on A. And it simply means that if we know what the value in A is, we can know what the value in B is. Okay. It does not mean that if we know what B is, we automatically know what A is. It doesn't work in reverse all the time. So for example, take a look here. Do I have anybody in the class with the same name as somebody else in the class? Let's see. Oh, good. I see I have two Suleimans in the class. Okay, so there's two Suleimans in the class. If I were to call out your student number, you would know which Suleiman I'm talking about, right? But if I were to say, I want the Suleiman in the class to do something, which one am I talking about? We don't know for sure because there's two, right? So your student number is an attribute that determines your name as far as the database is concerned, right? But your name does not determine your student number, right? So that's how the dependency works. It doesn't always work both ways. In fact, it quite frequently only works one way, which is very important that it should work only one way. Okay, so A determines B if the value in A determines what the value in B is. So if I say, oh, there's actually 3 Suleimans in this class. Is there more? Is there only 3? Let's see. And when I say in the class, I mean today on this call. All right, so there's 3, right? So if I had a student number, I could tell you which Suleiman I'm talking about. If I said, Suleiman, post a laughing emoji, which you just did, right? Which one of you am I talking to? Well, right, we don't know for sure, right? Okay, so that's how this whole functional dependency thing works. If you know A, then you know B, not always the other way around. All right, let's see. Okay. You could also diagram it like this, where you have a set in A that determines a set in B, right? By default, by the rules of the way that this whole set thing works, is B must be the same size or smaller than A if B is dependent on A. Right? Because there can be duplicates in B. Right? We could have 2 different values of A. For the example that I just gave, Suleiman, right? 2 different, actually 3 different student numbers all point to Suleiman. Right? So the number of student numbers in this class and the number of first names, distinct first names in this class, right? The number of student numbers is higher than the number of first names. So B must be the same size or smaller than A. That would be a good question for the upcoming midterm, I think. Yeah, may have to make a note of that. Okay. We will call the determinant whatever's on the left-hand side. So this is the determinant. It determines the value in the determinant. I'm sure there's another word for it, another determinant and determinant. Yeah, I'm not sure. I'll have to look that one up. All right. So some examples from our example set. Staff number determines position. If I know the staff number, I know the position. It does not work the other way around. I do not know. If I know manager, it could be any number of staff numbers. Right? So if I know the position, I don't know which staff person I'm talking about. Okay. Like I said, though, sometimes it does appear that this whole functional dependency might go both ways. So you might say, well, you know, the student number determines the name. Well, I guess the student number does in our situation, it doesn't go both ways, right? But in the example sample data, we may say staff number determines name, but name also determines staff number. So let's say name was first name and last name together. There are no shared first name, last name combinations in this class, right? You have Suleiman Turker Güner, and you have Suleiman Dadashov. I'm sorry if I said your name wrong. And Suleiman Altogan, right? Altogan. So you have distinct, everyone in this class has a distinct first name, last name combination, right? Yes. Yes, Murat. And we'll talk about that. Okay. So you say the staff number determines name, but staff number, like in our previous example here, let's go back. Staff number also determines position. And what we'll see is the way that we'll write that is staff number determines and all the columns that it determines. Okay. And it might appear that based on our sample data, slide 7, 7. Oh, that is 7. Where's what? Oh, I know why. Okay. All right. This example here, it might appear staff number determines name, name determines staff number. Like they both work both ways, right? However, there is one that does seem that it holds for all time, all possible values, right? And my guess is that as we start adding new employees, new staff to our system, there could be the possibility that the name might get duplicated, that we may end up adding another Joseph Lede to the staff. We may add another Murat Esh to our group, right? That seems more possible than adding another student number that's the same or another staff number that's the same, right? So what we do is we say, okay, let's identify this as being the functional dependency that holds for all possible values, that it's not, this one is not only true in the sample data, but it is also, of the two that are presented here, it is also the one that is more likely to stay true as we start adding new values, as we start adding new rows, okay? All right, and this makes sense. This would make sense. And in our student example that I gave, I hope you guys see that as well, that the combination of your first name, last name, even though right now it determines the student number, that may not be true for all time because we may add another student with the same name. Okay. All right. Okay. Right. Now, determinants, what we would like to have in all of our functional dependencies is the minimal number of attributes. So there may be more than one attribute on the left side that determines attributes on the right side. So when I say left side, right side, I mean here, left side, right side. Okay. But we want to have minimal number of attributes on the left side, and we call that a full functional dependency. Okay. Right. If B is fully functionally dependent on A, if B is functionally dependent on A, so in other words, and here instead of A and B are not single attributes, but a set of attributes. So kind of like what Murat brought up there, where you have multiple columns. A consists of one or more columns. B consists of one or more columns. Okay. And we will say B is fully functionally dependent on A. If B is first functionally dependent on A, so first things first, B must be functional. So all of the attributes in B must be functionally dependent on the combination of the attributes in A. Okay. This doesn't mean that some of the attributes in B are dependent on some of the attributes in A, although it could. But what it means is that all of the attributes that we're talking about in the set of B are functionally dependent on the combination of the attributes in the set of A. Okay. But not on any subset of A. So if A consists of 3 columns, and if A consists of 3 columns and B, some column in B is dependent on the 3 columns of A, but it's also dependent on just one of those columns too, well, then then we would not say that B is fully functionally dependent on A. Okay. This I think is best explained through an example, and we'll get there in just a moment, right? But let's talk about an example. Well, let's talk about an example from the staff relation. Okay. So we could say this is true, right? Staff number, the combination of staff number and staff name determines the branch number. Well, let's take a look. Is that right? From the staff relation, the staff number, staff name determines branch number. Yeah, that's true. Whenever we have a combination of SL21 and John White, we get B005. All right, SG37 and Beach gets B003. Now remember, just because there's duplicates over here, that's okay. In a functional dependency, we're just saying that anytime we see SL21 John White, we see B005, no matter where it appears. Okay. Yeah, each value of the combination is associated with a single value of branch. Sure, okay. However, branch number is really only necessary that we need to know what the staff number is. Right? We don't need both columns. We just need the staff number. Right? So what we would say is that because branch number is dependent on one of these, we don't need both of them. We call that a partial dependency. Right? So this is a partial dependency because it's not fully functionally dependent. Right? So the only one we would need would be the staff number determines branch. Staff number determines branch number. Okay. All right. Some characteristics we want to make sure we have here. All right. We want to make sure that there is a one-to-one relationship. On the left-hand side, the determinant, the thing that determines the other value, right? And those on the right-hand side. That any time a value appears in A, the same value appears in B. Okay. We want to know that it holds for all time, so it's not something that can change over time. The example we looked at here, that staff name determines staff number. Well, right now that's true, but it might not be true for all time. Right? So we want to make sure that when we're talking about functional dependencies, we identify those that hold for all time, not just current, based on sample data. Okay. And finally, the determinant has the minimal number of attributes, right? So we don't want to have this here. We would not want this dependency to exist in our set of functional dependencies. Right? Because this is not the minimal number of attributes over here. We could have staff number determines branch number and be done. Okay. So one more new thing I'll introduce you to is this idea of a transitive dependency, and then we'll take a break. Okay. So the idea of a transitive dependency is when we have inside of a relation where some set of A determines some set of attributes B, and B determines some set of attributes C. Right. And we call this a transitive dependency because we know that A determines C, okay, because A determines B and B determines C. So it's if we know the value in A, then we know the value in B. But if we know the value in B, then we know the value in C, which means that if we know the value in A, automatically we know what the value in C is. Okay. So if we look at an example, we have staff number determines staff name, position, salary, branch number, and branch address in the staff branch relation. All right, staff branch relation. Staff number determines all the others, right? Name, position, salary, branch number, branch address. But we also know that branch number determines branch address. So here's your A. This is A. This is B. And this is C. Right? So staff number determines branch number determines branch address. Right? We don't really need to state that branch address is determined by staff number. We don't really need to say that branch address is functionally dependent on staff number because it's dependent on another column in our list here. Okay. All right, so I need to make sure, so I'm gonna make sure that I say this again. Okay. Full functional dependency, no partial dependencies, right? So, or I shouldn't say. Let me rephrase that. Full functional dependency versus partial dependencies and transitive dependencies are going to be what we use to get us from what's called the first normal form to the third normal form of our database. Okay. All right. So we are going to work through full functional dependencies and transitive dependencies to start the process of normalization to get to the third normal form. And we'll do that as soon as the break is over, unless there are any questions or comments before I put you guys to break. No. Okay. So what we'll do is we'll take a break, and at 2:25 we will come back and we will start talking about how we do this whole normalization thing. Okay. I'll see you guys in 10 minutes.